Welcome to the Deep Dive. We're the show that takes the latest research and thinking and really distills it for you. Today, we're getting stuck into one of the big challenges in artificial intelligence. Genuine common sense reasoning, abstract thinking, that kind of stuff. Okay, so picture this. You get a series of visual puzzles, right? Each one shows maybe just a few examples, like 2 to 6 pairs of grids, colored pixels. An input grid transforms into an output grid, and the AI's job, figure out the hidden rule, the transformation function, just from those few examples, and then use it on new grids it hasn't seen. That's basically the Abstraction and Reasoning Corpus, or ARC-AGI. It's a test designed not to see what an AI knows from tons of data, but how well it can figure out a totally new puzzle on the spot with almost zero instructions. Now, for ages, the feeling in the AI world was, well, pretty skeptical. People thought traditional deep learning, even the huge language models everyone talks about, they just weren't cut out for ARC. Why? Because ARC needs something else entirely. It's all about few-shot learning, understanding the context, and figuring out new transformations from barely any info. It's not memorization. It's not just applying old patterns. It's a direct test, they say, of the efficiency of the learning process itself. It seemed like deep learning just hit a wall there. But then this paper came along, really shook things up. Don't throw the baby out with the bathwater. How and Why Deep Learning for ARC by Cole and Osman. And their claim was pretty bold. Deep learning, if you really push it, if you leverage it fully, can get state-of-the-art results on ARC. So our mission today, unpack this, look at the academic thinking behind it, the innovation, and show you how they kind of rewrote the rulebook for deep learning in abstract reasoning.
Yeah, it's fascinating because this work really shifts the goalposts for deep learning benchmarks, doesn't it? Instead of just measuring, what a model's memorized from its training data, ARC measures how efficiently it can learn something totally new, in context, from almost nothing. And that really makes you ask, what is machine intelligence? Is it just recalling facts, or is it this ability to adapt on the fly?
That's a great way to put it. So if ARC is like this fluid intelligence test for AI, measuring its ability to think on its feet, what makes it so fundamentally different from, say, recognizing cats and dogs in ImageNet? Millions of images there.
Right, it's a totally different game.
Yeah.
ARC is fundamentally unlike big data sets such as ImageNet. On ImageNet, models often pick up on statistical quirks or just reuse features they learned during pre-training. ARC, though, explicitly tries to limit the degree to which the model can rely on pre-trained knowledge or zero-shot performance. It puts a heavy emphasis on the need for contextual reasoning during the evaluation. For every single riddle, the AI has to learn a new skill, a new transformation, right there and then.
So it's less about, that's a cat, and more like, oh, the rule is turn squares into triangles, so now I need to apply that specific rule to this new circle.
Precisely. And the authors point out that ARC problems are more perceptual and qualitative than quantitative in nature. What that means is there's a near infinite number of possible transformations. So just trying every possible rule, like a brute force search, that becomes completely impractical. It's not about crunching numbers. It's about grasping a visual concept, an abstraction.
Okay, so what does an AI need to actually do this? What capabilities are essential for tackling these kinds of puzzles? Sounds like it needs to be pretty smart, pretty agile.
Absolutely nimble. An effective ARC solver needs a few key things. First, something called associative learning. That's the ability to connect the dots, not just within one input-output pair, but across all the example pairs to figure out the big picture, the overall rule.
Okay, seeing the relationships between all the examples.
Exactly. Second, contextual reasoning. The model absolutely must learn a new transformation from just those few examples given for that specific task. It can't just pull a general rule off the shelf.
Got it. Learn in the moment.
And third, holistic processing. This is crucial. A good ARC solver has to process all grid pairs in unison. Look at them all together. That lets it spot the crucial shared patterns and transformations, which is really different from simpler models that might look at examples one by one or just average them out somehow. That loses all the important relational stuff.
Like seeing the whole forest, not just the trees, as you said.
Precisely. You need that holistic view to understand the underlying ecosystem, the hidden rule.
Okay, this is where it gets really interesting for me because, as you said, they're not just making the model bigger, they're actually changing how deep learning works when it's trying to solve the problem, teaching it to learn how to learn right then and there. What's the core innovation? What's the academic breakthrough enabling this?
Right, the absolute core innovation here is their commitment. They're fully committing to deep learning's capacity to acquire novel abstractions. And how do they do that? By treating both the neural network and the optimizer the thing that trains the network, as integral components of the inference process. It's not just about using a pre-trained network anymore. This allows for on-the-fly neural network training, right when the test is happening,
Yeah.
which is what fosters that real generalization to tasks it's never seen before. It's about making the model dynamically optimize itself while it's problem-solving for each riddle.
Wow. Okay, so the model isn't just a fixed tool anymore. It's more like a tool that sharpens itself, adapts itself as it's being used for a specific job. That feels like a big shift.
It's a huge shift. And it leans heavily on how they use in-context learning, ICL, especially what we see in large language models. There's growing evidence that LLMs are actually pretty good associative learners. They act like versatile pattern recognition tools, and they can even identify complex underlying structures, like what researchers call probabilistic context-free grammars. That innate ability to spot and use relationships between inputs, that's critical for cracking ARC.
And their specific model choice, long T5, that seems deliberate too, right? Why long T5?
Yeah, very strategic. Long T5 was picked because it has a long context window and, importantly, non-causal attention mechanisms within the encoder. This unmasked attention is vital. It lets each token simultaneously attend to the entire input sequence right from the start. So the model sees the whole ARC riddle, all the pieces all at once immediately, gets the full context, like seeing the whole game board instantly.
That makes sense. Now, I also saw they made a decision that seems harder. They decided to generate the output grid directly as just a sequence of pixels and colors, rather than having the model generate, say, code that would then create the grid. Why go the harder route?
It does sound counterintuitive, doesn't it? But they found this direct output approach, even though it seems much harder, was actually much more explicit and well-defined. And crucially, it performed better in their early tests. Trying to get the model to generate code adds another layer of complexity, making sure the code is syntactically correct, making sure it actually does what's intended. Generating the output directly just streamlines things, focuses on the visual goal.
Okay, that clarifies that. And then there's multitask training. Were they just throwing more data at it, or was there a specific strategy behind mixing ARC data with NLP data sets like tiny stories or squad, and even math and science stuff?
Oh, definitely a deeper strategy. Mixing ARC with diverse data sets, NLP, math, science instructions, even multimodal reasoning like C-lever, forces the model to manage multiple modes and contexts simultaneously. This constant context switching is key. It makes it harder for the model to just memorize stuff and pushes it towards genuine contextual reasoning. It basically trains the model to be flexible, to be an adaptive problem solver, not just a one-trick pony.
Builds mental agility, kind of?
Exactly. And then there was that really interesting finding about code pre-training. Why did training on coding tasks give such a bigger boost for ARC compared to just adding more language data? Yeah, that was a critical insight. Really highlights the academic depth here. They found training on code gives a more pronounced performance boost on ARC than merely adding multitask training derived from language or NLP domains. The reason seems to be that code demands meticulous attention to detail and context. It fosters a better focus on context and hierarchical thinking. You can't just memorize your way through coding. You have to understand the logic, the structure. So code data seems to instill these valuable logical priors, this way of thinking that's less ambiguous, and that transfers surprisingly well to abstract visual reasoning puzzles like ARC.
That's really fascinating, how the type of training data shapes the AI's core reasoning abilities. And to get more ARC data, they used automatic riddle generators. How did that work, and what's this idea of overspecification?
Right, they needed more data, so they used programmatic generation, inspired by domain-specific languages, to create more ARC riddles automatically. They used a clever dual prediction strategy. The model had to predict both the final output grid and the name of the underlying function or rule used to generate it. And overspecification was vital here. It means making sure the generated riddles had just enough information so the model could figure out the single intended solution without ambiguity. It stops the model from getting confused by multiple possibilities or just memorizing fuzzy patterns. It forces it towards learning cleaner, more generalizable rules, like giving it a clear path.
Okay, so we've got this meticulous pre-training, the right model architecture, but the really mind-bending part seems to be what happens at test time. You said they're essentially teaching the AI during the test, giving it practice right before the real thing. How do these test time techniques work?
Yes, this is really where the magic happens, optimizing inside the evaluation loop. Two main game-changing techniques here. The first one is test time fine-tuning, or TTFT, and this is a really Profoundly academic idea applied very practically.
Okay, break down TTFT for us. What's the actual process?
So during the evaluation, when the AI is looking at a new riddle, they take one of the example input-output pairs provided with that riddle, one where the answer is known, obviously, and they repurpose it. They treat it like a new mini training example. Then they augment it, change colors, rotate it, flip it, shuffle examples, creating more synthetic data from that specific riddle's examples. And then the model does a very brief round of fine-tuning, updating its own parameters using this freshly created riddle-specific data. Then it makes its predictions for the actual test grids it needs to solve.
Whoa. And the goal is iterative reframing, like letting the AI rethink its approach based on the riddle itself.
Exactly like that. TTFT lets the solver reevaluate and iterate on potential solutions. Just like a person might pause, look again, and refine their thinking if their first idea doesn't quite fit. It helps the model reframe its approach if its initial pass, maybe due to limited attention or inadequate depth of processing, wasn't quite right. Getting the right framing is critical for perceptual models, apparently. So TTFT gives it this dynamic way to adapt its internal frame based on immediate feedback from the riddle itself. They even went for full parameter updates during this quick fine-tuning, choosing simplicity and reliability to guarantee the power to generate the needed abstractions for these genuinely new tasks. It allows for hyperspecialization, leading to those pixel-perfect outputs.
That's seriously clever, making a static model behave dynamically. Okay, what about the second technique? AIRV. Augment, Inference, Reverse-Augmentation, and Vote. Sounds like a mouthful.
It does, but the concept is quite elegant. AIRV is used after TTFT. It's another form of test-time augmentation. You take the input riddle, apply spatial transformations, rotate it, flip it, etc. Then you run the now TTFT-tuned model's inference process on each of these transformed versions. You get predicted output grids for each transformed version, and then you reverse the transformation on the output grid to get it back to the original orientation.
Okay, so you're essentially looking at the puzzle from different angles.
Exactly. You gather multiple predictions this way from these different spatial perspectives. Then you use a voting system. The output grid that appears most frequently, or maybe the one the model is most confident about across the different augmentations, wins. It's the final answer.
Like getting a consensus from different viewpoints to find the most robust answer.
Precisely. It amplifies strong, consistent solutions and filters out noisy variants. Which makes a lot of sense for ARC because remember, each riddle has precisely one correct solution. It's a bit like how AlphaCode used clustering to pick the most common program generated. And underneath all this, during the actual generation of the output grid, they also use beam search, which is a smart way to explore multiple possible output sequences step by step, keeping the most promising ones and discarding the bad ones to find that single best answer efficiently.
So taking a step back, TTFT and ARV together, they represent this move away from just relying on what the model already knows towards a system that actively adapts and refines its reasoning during the task.
Absolutely. It's a fundamental shift. It acknowledges that real intelligence, or something approaching it, involves this iterative refinement, self-correction, not just spitting out pre-memorized patterns. It's a very sophisticated, very academic take on AI innovation.
Okay, the results must speak for themselves then. You mentioned the state-of-the-art performance. Tell us about the numbers, especially considering those tight compute limits, 2 hours on one GPU.
Yeah, the results are pretty stunning, especially under those constraints. Their base long T5 model, fully trained with their pre-training strategy, in zero shot, so just using the pre-trained model, it got 5% accuracy on the private test set, which is, not great.
Okay.
Add AIRV, the voting mechanism, that jumps to 13%, a decent improvement. But then add TTFT, the test time fine-tuning, with AIRV, it skyrockets to 39% accuracy. That's a huge leap.
39%, that's massive.
And it gets better. A later, more optimized version of this same core approach. It achieved 58% on the ARC-AGI private test set in 2024. That won them first place in the 2023 ARCathon competition.
58%. Wow. That's incredible progress on such a hard benchmark.
The quantitative gains are just huge. AIRV alone gave up to a 260% relative boost over zero shot, and TTFT added another 300% gain on top of the baseline, plus AIRV.
But you mentioned something counterintuitive earlier about model size versus the pre-training. Can you unpack that? It wasn't just bigger is better.
Right. Initially, it looked like bigger models did better in zero shot, or with just AIRV, even with less training data, which fits the usual deep learning story. Bigger model, more expressive, better results. But, and this is the really key academic insight, while size helps a bit on its own, they found that extensive ARC pre-training is indispensable for achieving state-of-the-art performance with TTFT. You couldn't just scale up the model and skip the hard pre-training work if you wanted top results with the fine-tuning.
So the pre-training wasn't just about seeing more examples, it was doing something deeper to enable that test time learning.
Exactly. This leads to their concept of the sedimentation process. It's a really profound idea. The ARC pre-training isn't just about the model accidentally memorizing or leaking solutions. Instead, it deeply embeds foundational knowledge, core knowledge priors, like just understanding the input-output structure of the grids. And it also embeds more subtle but highly important priors, things like a preference for simpler rules or the drive to check a hypothesis against all the examples. This sedimentation, where these useful biases get baked into the earlier layers of the network during pre-training, actually frees up capacity. It makes more room for test time features to emerge during that brief TTFT fine-tuning.
So the pre-training builds the intuition, the foundation, which then allows the model to be more creative and flexible when it fine-tunes on a new specific problem.
You've got it. It's like building a really solid base of common sense about how these puzzles work, which then allows for true innovation and complex task-specific reasoning on riddles it's never encountered before. It sets the stage for the AI to efficiently learn how to learn new abstractions.
That's a really deep insight, and managing to do this within those strict compute limits makes it incredibly efficient compared to other methods.
Definitely. It highlights this nuanced view of learning. It's not about cramming answers, but building the right inductive biases so the model can discover solutions efficiently when faced with something novel and abstract. That sedimentation idea is central to their innovation. It shows how deep learning can be guided towards more fluid intelligence.
It really makes you appreciate how clever this is. It's not just scale, it's fundamentally innovating on the learning process itself. How does this stack up against other ways people have tried to crack ARC? Where did they fall short?
Well, it really puts other approaches into perspective. Take standard, off-the-shelf LLMs, even powerful ones like GPT-4. They call these frozen LLMs because you don't fine-tune them for the task. Their performance on ARC is pretty limited, maybe single digits on the public test set for GPT-4. They can recognize some patterns, sure, but they lack that deep abstraction and, crucially, the dynamic reasoning. They can't adapt their internals at test time like this approach does.
So just prompting a big model isn't enough because it can't fundamentally change its internal rules on the fly for this specific puzzle.
Exactly. Then you have things like neurosymbolic approaches or program synthesis, like Codit, or methods inspired by Dreamcoder. These often need significant human guidance. They tend to struggle with the very perceptual, visual nature of ARC, and they find it really hard to define the almost limitless range of possible transformations using explicit code or formal languages. They sacrifice that flexible implicit learning for explicit rules that often just can't capture ARC's ambiguity.
Right. Trying to code every possible visual transformation seems impossible. What about just pure search, like the IceCuber method that won back in 2020?
That was impressive for its time and effective on some tasks. But brute force search is computationally very expensive, and it's generally less, well, generalizable across the whole wide, weird, ambiguous range of ARC riddles compared to a learning-based perceptual approach like this. These other methods often run into broader issues, the paper points out. Comparisons made without fair compute limits, poor generalization, not reasoning contextually across all examples, not focusing enough on the perceptual aspect, and sometimes evaluating only on public data, which might inflate scores.
So the edge for Cole and Osman's work is really this specific combination.
That's right. It's the focus on broader perceptual reasoning as the core component, plus the absolute necessity of fine-tuning this perceptual reasoner on ARC tasks for each task at test time. And they've showed it works strong generalization on the unseen private test set and superior computational efficiency. It's a really elegant mix of deep learning strengths with smart, adaptive learning strategies.
It really underscores that maybe the path to harder AI challenges isn't just more data or bigger models, but smarter learning systems. Systems that can actually learn new skills dynamically.
Exactly. It feels like a significant step towards more fluid, adaptable intelligence in machines. And it's a great example of how innovation is still driving deep learning forward in really interesting ways.
Okay, so this deep dive has really shifted my perspective on what deep learning might be capable of, especially around abstraction and common sense. The core idea, the breakthrough seems to be fully embracing deep learning's ability to abstract, but unlocking it through that clever test time learning and the really careful foundational pre-training. It's about coaxing deep learning to adapt and innovate, not just repeat patterns. So for you listening, the big takeaway, maybe it's this powerful idea that AI's ability to genuinely figure things out in totally new situations, that real learning efficiency, that novel abstraction is actually starting to unlock. It's not just about knowing things, it's about how the AI learns to learn right when it needs to, even, right there during the evaluation. And that leaves us with a question, doesn't it? What other kinds of really complex abstract problems, ones we thought were way out of reach, might suddenly become solvable if we keep pushing this learning at test time idea, pushing the boundaries of how and maybe when AI gets its deepest insights? Something to think about. It could really reshape our whole understanding of machine intelligence down the road.